Hello and welcome to the solutions video for our Unit 2 unit exam. Just have to find it here. So in our first two, we are converting this vector into components. Now that direction 12 degrees north of east puts it in standard position. So we just need 6.7 units and north of east. So flipping to our calculator. First thing we do is make sure we're in degree mode. Now for the x component, we're going to want the horizontal piece, so that's our cosine. And for our y component, we need the vertical piece, that's our sine. So these are the two values we have. So our horizontal component is 6.55 and the vertical is 1.39. So number 3, which measurements are vector quantities? Car travels north at 30 kilometers an hour. That is a vector. A ball is thrown up in the air and takes 23 seconds to hit the ground. Time is a scalar. Length of a driveway is 250 meters. We don't know which direction it's facing. A student travels westbound for 800 meters walking to school. This is a vector. 80 newtons pushes down. Vector. Gravity accelerates an object at negative 9.81 meters per second. Even though it's negative, there's not technically a direction on that. But travel downward on an elevator, that's the other one. So the question is, which of these is our vector? So in this case, we know the 80 kilogram man is traveling downwards, but 80 kilograms is a mass. That is a scalar quantity. So this one would be 6. And actually, come to think of it, up here, we've got 6.7 units. That's 2 sig digs. I did too many sig digs on those numbers. All right. Number 4. A cyclist pedals at a constant velocity of 12 meters per second for 37 minutes and then 17 meters per second in the same direction for 14 minutes. The average velocity of the cyclist for the entire trip is, well, the average velocity is total distance divided by total time. We need the distances here. So our 12 meters per second at 37, or for 37 minutes, we've got 12 meters per second times 37 minutes times 60 seconds per minute. So 12 times 37 times 60 is 2,600 or 26,640 meters. Our second leg of the trip is 17 meters per second for 14 minutes. So that's 17 meters per second, 14 minutes, on our same 60 seconds per minute. 17 times 14 times 60. That's 14280 meters. And now we're asked for meters per second, and everything here is north. So our total distance traveled is in our numerator, our total displacement, but it's all northbound. And in our denominator, we have our 37 plus 14, both minutes, times 60 seconds per minute. And then our minutes will cancel. We'll have meters per second. So doing that in our calculator, we end up with 13.37259 or 4902 meters per second, or to our three significant digits, 13.4. All right, our next question. An elevator travels 28 meters upward to the 8th floor in 9.5 seconds, waits for 20 seconds as somebody gets on, then travels down 10 meters to the 5th floor at a speed of 3 meters per second. Average speed is total distance over total time. The distance doesn't care about direction. So that's a total of 38 meters. And our time, we've got our 9.5 seconds or 20 seconds. We weren't given how much time it takes to go down, but it's going to be 10 divided by 3. So that's 3.33 seconds. We add those up, we have 32.83 repeating seconds. And we're going 38 meters in that much time. Works out to 1.2 meters per second. Average velocity, the direction does matter. So our total displacement is 18 meters up. But we have the same total time of 32.83 repeating. So that's 0.55 meters per second. Again, in the upwards direction. All right. So at a baseball game, the batter hits the ball straight up. And it goes into the air at a speed of 34 meters per second. The ball is hit near the ground. 1.05 seconds after the batter hits the ball, it will be moving at a speed of... So for this one, our velocity as a function of time is our initial velocity plus acceleration times time. We could also do that from the definition of acceleration. Final minus initial over time gives us our final velocity is our initial plus AT. So our initial here is 34. We're told to go straight up in the air. So 34 plus a negative 9.81 times 1.05 gets us 23.7. So the ball will reach a maximum height of how many meters above the ground? Well, in that case, we are letting VF equal 0. And to figure out how much time, or even better, we can go VF squared. Okay. Equals VI squared plus 2AD. So our D, our displacement, is going to be VF squared minus VI squared all over 2A. And they say it's hit near the ground. They're saying we can assume the initial speed, or the initial position was 0. We're going to the top of the arc, so that's 0 meters per second up there. Our initial speed was 34.0 meters per second. It's 2 times a negative 9.81 meters per second squared. So we have a negative 34 squared divided by a negative 19.62, which is 58.9194693 meters per second. Or to these significant digits, 58.9. Now, number 7. This one gave people some difficulty. We want to figure out which zones each of these are in. In our first one, we see 0 as a dashed line. I'm going to zoom in so we can better read these graphs. So here's our velocity coming up. 0 is a dashed line above it, and our line is straight. So this is the velocity versus time. The straight line means we have a constant acceleration, and the velocity is entirely negative because it's below r0. So our slope is positive, which means we have a positive acceleration, so it puts us in the right-hand column. It's moving left because our velocity is negative. That puts us in the top row. So we're in space 3 for our first column. Number 2, our slope is 0. So our acceleration is 0. Our velocity is positive. So we have uniform motion moving right. So this is an 8. Now our third one. Now this is curved. So there is some acceleration involved here. Our displacement is negative the entire time, but it's getting less negative. So this is to the left of the origin, but moving to the right. And it's decelerating as we're getting there. So it is moving to the right, but which puts it in the bottom row, but it's negative acceleration because it's getting pulled down. Our positive velocity, but negative acceleration because that velocity keeps decreasing. So this is a 7. And in our final graph, our dt graph has a constant slope. That means we have a constant velocity and 0 acceleration. D is positive, so it's on the right, but that negative slope means it's moving left. So it's moving left, which is negative, with uniform motion, which is box number 2. All right, that's next, and then we'll go back to resetting our zoom. Oh, which apparently is not easily reset. We have to manually click as many times as we did. I mean, I would have clicked as much had I known that. All right. A hockey player chases a puck as it slides towards an empty net. The hockey player is 5.61 meters away from the puck when the puck is 9.54 meters away from the net, as shown below. The puck is moving toward the net at a speed of 3.60 meters per second. In order to reach the puck before it slides into the net, a player must skate at a constant speed of how many meters per second? So first off, we need to figure out how much time it takes the player to get there. And if he's getting there or if the puck is there before the net, we want to make sure the player gets there faster. So we could time it out so that the player and the puck meet exactly at the net. So the puck will cover those 9.54 meters at 3.60 meters per second. So 9.54 meters at 3.60 meters per second gives us 2.65 seconds of transit time. That player has to go this combined distance. So the player is going 5.61 meters plus 9.54 meters divided by 2.65 seconds. And that is 5.7169811132 meters per second, or to our 3 sig digs, 5.72. Multiple choice 3. A vacationer is walking at a speed of 1.5 meters per second on the deck of a cruise ship that is sailing at a velocity of 7.5 meters per second west. Relative to the shore, the magnitude of the resultant velocity of the vacationer if he heads north is. If he's heading north, then he's moving perpendicular to the direction of the boat, which means we are using the Pythagorean theorem to add these together. So it's a squared plus b squared, we take the square root. If we do that, it's definitely going to be more than 7.50, so that eliminates a and b, and it's going to be less than just adding the two numbers up, which is c, so our answer is going to be D. Now, a stuntman drives a motorcycle at a speed of 95 kilometers an hour from the horizontal top of a 3.5 meter high wall. How far from the wall will the motorcycle land on the ground below? So this is two parts. It's projectile motion, horizontally launched. We need to connect the two with time. So vertically, the initial speed is 0, and it's just dropping 3.5 meters. So our D equals VIT plus 1/2 AT squared. That term goes to 0. So our time, when we solve for it, is root 2d over a. He's going to drop 35 or 3.5? 3.5. 3.5 meters at negative 9.81 meters per second squared. So that's the square root of 7 over negative 9.81. So it's about 0.8447233833 seconds. So then the distance is the speed times the time. It's going 95 kilometers an hour. And then we can convert that. We have, so 1 hour. I'm going to erase that, make it legible. 1 hour over 3,600 seconds. 1 kilometer, 1,000 meters, times 0.844, etc. seconds. So our distance works out to about 22.2913115 meters, or 22 meters. Number 9. Landing probes on Mars is made more difficult by the fact that the atmosphere is extremely thin, with a pressure of 0.6% of Earth's. Frankly, everything we need to know is in the second paragraph. In one test of a probe's airbags on Earth, an airplane flying at a speed of 380 kilometers an hour accidentally drops the probe from a height of 150 meters. Or not accidentally, horizontally. So in other words, it is being dropped, but it will fall with that speed of the aircraft. So it will continue moving at 380 kilometers an hour horizontally as it falls. So we've got our same two-step algebra. It's identical algebra to the previous problem. So our t is going to be the square root of 2d over a. So 2 times negative 150 meters over negative 9.81 meters per second squared. So negative 300 over negative 9.81, and we take the square root of the whole thing. It takes it about 5.530012636 seconds to fall. And then that distance is our velocity. We can shortcut our conversion factors, dividing it by 3.6. We'll turn that into meters per second. Multiplying all that together, it's a 583.7235556 meters, or, to the 3 signigs in the question, 584 meters. A ball is hit with a velocity of 25 meters per second and an angle of 35 degrees with the ground. How far from where it was hit does the ball strike the ground? All right, so this is another two-part problem. So first we have to use the vertical component to figure out how much time it spends in the air, and then the horizontal component to figure out how far it goes. So our vertical component, it starts with 25 meters per second and an angle of 35. So 25 meters per second times the sine of 35 degrees is our initial velocity. Which is roughly 14.33941091 meters per second. Actually, in this case, we can go from here directly to the time and the total time of flight, because we don't care how high it goes. So we can use our acceleration as the final minus initial over time to say that our time is the final minus initial velocities over the acceleration, where our final velocity will be negative 14.3394191 meters per second, and our initial is the positive version of that number because we have that symmetry in the absence of air friction, and our acceleration is negative 9.81 meters per second squared. So the total time is 2.9234273 seconds. Now the horizontal displacement is velocity times time. Our horizontal component of velocity is 25 meters per second times the cosine of 35.0 degrees times our 2.9234273 seconds. All of which works out to 59.86828624 meters, or 59.9 meters. Now, we've got our two-part finisher. This is why I was holding off on returning the tests, because this is the same question on both the test and the makeup test. The rest are different, with randomized numbers, of course. So, you are one of the first human beings to land on SETI Alpha 5, and you need to understand how strong the local gravitational field is in order to properly plan your nutritional needs. You find a rock face you can climb, and you can drop an object of mass 18 kilograms from a variety of height, timing its descent. This is the data we collect. So how far we dropped it from, and the time of descent. So this is the same data we had for this unit's lab, which is due Monday. If you wish to use the slope of a graph to calculate g, the local acceleration due to gravity, which graph should you make? So if we do t versus d, is that going to work? Well, in this case, we are doing an object in free fall. So we have d is vit plus 1/2 at squared, but our vi is 0. So d is 1/2 at squared. Our a, the acceleration, is where our g is going to show up. So we're going to pull that out. That acceleration should be g. It's attached to a variable, so it cannot be the y-intercept. So in our y equals mx plus b form, with no vi, and frankly, even if we had a vi, that would break everything, because that's not constant. We have no constant being added here, so our bi is 0. Our y is going to be our displacement, and our x is going to be this term with that 1/2 at squared. We pull the a out, everything that's left behind is our x. So that is t squared over 2. So d has to be our y, and t squared over 2 has to be our x. Now we need to find the acceleration of gravity on SETI Alpha 5. So this is where we start using the linear regression on our calculators. So let's flip back to that. Now, in order to do this, we're going to have to go into our lists and edit them. So we go Stat to pull up this menu. We edit our lists. We say they have data in them already, so I'm going to clear that data. So we're starting from scratch. Our x values, we said, are t squared over 2. So we can enter them as t squared over 2. You'll notice I typed in the bottom our first time, 1.63 squared divided by 2. We can enter all of our times that way. And here's all of our x's. Then we go to our second column. Here's where we enter the y's, and these were all multiples of 13. So there we have everything entered. So now that we have this, we have to do our linear regression. So we hit our stat button again. We go to our calc menu. We go to our linear regression option. Notice there's two of them. 4 and 8 will both work as long as you recognize A is the slope of number 4 and B is the slope of number 8. By default, list 1, where we put our x, is our x list, and list 2, where we put our y's, is our y list. If we want, we could come down to our store regular equation, hit our vars button, go to our y variables, pick a function, and pick y1. So once this does the calculation, it will put our equation in y1 on our graph. And we can calculate. You may just see the a and b. Right now in the mode on this calculator, I've got the statistics numbers on. But the key here is that our slope comes out at about 10.4377707. So it's coming out at 10.4 meters per second squared. Strictly speaking, this is all we need to do. We may also want to come to our plot. Notice that it's populated with that graph. We can push up, turn on plot 1, so that we know that our data points are there. We hit our zoom menu. Option number 9 will zoom to our statistics. And this does look like a straight line. So it appears to have been correctly linearized. Just as a bit of a sanity check. So then our acceleration due to gravity is 10.4 meters per second squared. And this should finish the test. So that's the 100% we're looking for.